Hello, lecture 2 on convolution. Okay. Okay, so last time what we did was we introduced the convolution, well, gave the formula for both continuous and discrete time convolution, and then looked a little bit carefully at continuous time convolution and talked about the notion of convolvability of a pair of signals f and g, under which their convolution is well defined, and gave some examples of pairs fg that are convolvable. Okay, so in our description of pairs of spaces for which the pairs are convolvable, we sort of saw some very particular properties of that f and or g should have in order that their convolution be well defined. And we also saw that in the cases we looked at, the convolution itself had properties. It was in some predictable space of functions. And connected with that is a notion of what's called continuity of convolution. Okay, and I think before I get to the specific discussion of things pertaining to convolution, what I want to do is something we haven't done thus far, which is talk about continuity in general. And for our purposes, the constructions I'm about to give here are not entirely satisfactory, but they give some context for the continuity we're going to talk about when we talk about continuity of convolution. Okay, so so first let's talk about continuity of linear mappings. And this is going to be, I'm just going to do this in the setting of linear mappings between normed vector spaces. Okay, and as I say, so not all of our spaces of signals are normed, right? When we talk about the locally integrable spaces, for example, or the spaces of continuous functions not defined on necessarily compact intervals, those spaces don't have norms. They have a family of semi-norms that define their topology. And so this discussion of continuity will not be entirely satisfactory, but it'll give us something to lean on. Okay. All right. So continuity is has the usual definition in terms of epsilons and deltas. So maybe I'll give it here, just so we make sure that we understand that the notions we know from elementary real analysis also apply to normed vector spaces. Okay, so let's let U and B be normed F vector spaces. And let F, let's say, be a mapping from U to V. Not linear necessarily at this point. Okay, we say F is continuous at some point u naught if, and it's the usual definition. Okay, so for each epsilon, there exists a delta such that if u is within delta of u naught, then f of u is within epsilon of f of u naught. Sorry, this will be now u and v. Okay, so that's the usual notion of continuity. All right, so that applies here. So I should say that in the cases we talk about that are not normed, they're only semi-normed, right? So we have families of semi-norms that define the topology. Then you have to this should hold for every pair of semi-norms. Okay, so let me say this carefully. So you fix a semi-norm for v. Okay, and for that semi-norm for v and for that epsilon, there exists a semi-norm for u and a delta, so that this being less than delta implies that this is less than epsilon. Okay, so there exists a semi-norm. Okay, so that's how you adapt those definitions. And the other way to do this, of course, is to use sequences. So the usual notion that a mapping is continuous at u naught, if you take a sequence in u which converges to u naught, then continuity is exactly the requirement that the sequence f applied to that sequence converges to f of u naught. Okay. Now that characterization of continuity in terms of sequences, that also applies to all of our spaces defined using semi-norms. And I don't want to imply that anytime you have a topology of a vector space defined by semi-norms, that continuity is equivalent to the sequential characterization that I just talked about. That's not true. But for the ones that we're talking about, it is true, for reasons which have to do with things that go well beyond what we're able to talk about in this course. Okay. So the sequential notion of continuity in this course suffices. And we also saw a representation of that when we talked about distributions, right? So we were able to characterize distributions and the topology on spaces of distributions and test signals by using sequences. Okay, so that's fortunate, but that's not always the case. Okay, and so then there's a not difficult result that characterizes. So maybe what I'll do first is give another definition. Okay, so we'll say that f is bounded if f of b is bounded in V when B is bounded in U. Okay. And so I guess the notion of what a bounded set is clear, but maybe I'll say it anyway. So a subset B of a normed vector space is bounded when the norm restricted to B is a bounded function. Okay. So we have these two notions of bounded and continuous. Now, we certainly expect that there should be, even just in for functions defined on the one-dimensional vector space F, or take F to be R, you can easily come up with examples of functions that are bounded but not continuous, or continuous but not bounded. So generally one expects there to be no relationship between these things, but for linear mappings, there is a relationship. Okay, so so if you have is a linear mapping between normed vector spaces then there's a bunch of equivalent statements. Okay. All right. So L is continuous. Okay, so continuous here, of course, and as always means continuous at every U. L is continuous at 0. Okay, so for linear mappings, it suffices to check continuity at the origin. L is bounded. So maybe let me reorder these. Maybe let me say here that L is uniformly continuous. Okay, if Uj is a sequence in U, converging to 0, then L, the sequence L of Uj converges to 0 in V. Okay. And there's more you could say here, I guess, but let me just sort of round it out with saying that L is bounded. Okay, so There's a bunch of equivalent statements for continuity of linear mappings. Okay, so linearity is important, and normed is important. Okay, so if you relax either of those assumptions, then generally the result, not all of the conditions are true. So for linear mappings between F vector spaces with topologies that don't necessarily come from norms, but come from semi-norms, like we've talked about, then everything here, so let's see, so the first three are always equivalent. Okay, not just in norm spaces, but in spaces whose topology is defined by a collection of semi-norms. But it's not generally true, and you know, so and the first, somebody says, so generally the first three imply both 4 and 5. Okay, but the converses are not generally true. Okay. However, for all of the vector spaces of signals that we're going to deal with here, so that means, for example, the locally integrable ones, then these 5 things are actually all equivalent. And again, that has to do with very specific properties of the topology defined by that family of semi-norms. Okay. All right. Okay, so so that's continuity of linear mappings. So let me just say the proof of this is kind of more or less by hand, and there's nothing really involved in the proof of this that's any different from what you might prove in an elementary analysis course. Okay, so one more thing I'll maybe say is this: is that every linear map L from U to V is continuous if and only if the U is finite dimensional. Okay, so there's 2 parts of this. You know, one is that if U is finite dimensional, then every linear mapping is continuous. Doesn't matter what V is. But the converse is also true, which is to say that if U is infinite dimensional, then there are always discontinuous linear mappings from U into V. And again, it doesn't matter what V is. Okay. All right. So what we're going to talk about are not linear mappings, because convolution, you know, it can be thought of as a linear mapping if you fix one of the arguments of the convolution, but as a function of both f and g in the convolution of you know, f star g, that mapping is bilinear. Okay. And so to give again just a little bit of flavor for that, let's talk about continuity of bilinear mappings. Between normed vector spaces. Okay. And so a bilinear mapping from U cross V into W. Okay, and of course, UV and W are F vector spaces, so not necessarily normed, because I'm just talking about algebra now. All right, so these are just vector spaces. So a mapping is bilinear. So it takes 2 arguments, one from U and one from V, and gives me something in W. So a bilinear mapping has the property that it's linear in each entry. So let me say exactly what that means. Okay. Okay, so it's a mapping B from U cross V into W such that, okay, so there's, okay, such that the mapping U goes to B of U V naught is linear for each V naught. And V goes to B of U naught of V is linear for each U naught. Okay, so it's linear in each argument. Okay, so then you can characterize a continuous bilinear mappings between normed vector spaces as follows. Okay, so let U V and W be normed F vector spaces. And let B U cross W be bilinear. Okay. Oh, so I should have said here, and I knew I'd forget something here. Let me maybe, so bounded here. So this is the definition I gave for bounded, but for bounded linear maps, there's sort of a, so let me just sort of add this here. Okay, there exists an M positive such that the norm of L of U in V is less than or equal to M norm U in U, and this is true for every U in U, okay? So sometimes you'll see this characterization given as the definition of bounded, but the definition I gave of bounded is meant to apply for maps that aren't necessarily linear, and so in the linear case, oftentimes this is given as the definition. Okay, and I wanted to say that because I'm going to give a characterization of continuity of bilinear mappings, which looks an awful lot like that. Okay, so then B is continuous. Okay, so there's some stuff that I'm leaving out here, right? So what does it mean for a mapping to be continuous as a mapping from the product here into W? Okay, and so really what this comes down to is, the usual definition of continuity is you want to choose a small neighborhood about a point here, so that if you choose a small neighborhood about something that maps to that point, then it maps into the small neighborhood there. So what my point is that you need to say what small neighborhoods in U cross V look like, and they look like small neighborhoods in U cross small neighborhoods in V. So that's how you define continuity from a product like that. Okay, so I'm not covering this. This isn't a full-blown topology course as much as I wish it was. Okay, then B is continuous if and only if, and so this is where we get a characterization that looks rather like the one for linear mappings. Okay, so that B applied to U, V, okay, so this is in the W norm, is less than or equal to M, U, V, like that, okay? All right, so that sort of finishes my aside about continuity of general, linear, and bilinear mappings, okay? So now let's talk about convolution. And the reason, like I said, the reason I wanted to talk about these is that we'll see this kind of a condition showing up in our characterizations of continuity for convolution, okay? All right, so all right, so continuity of convolution. Okay. All right, so we had these spaces that we talked about of convolvable pairs, okay? So last time we had 4 sets of conditions on F and G to ensure that FG is convolvable. Okay. And just to remind you, those conditions are sufficient, but definitely not necessary. Okay, and as I said last time, I'm unaware of useful, necessary, and sufficient conditions for convolvability in generality. So one almost always talks about convolution, where if you want to talk about function spaces and convolution, you typically choose a space where F lives and a space where G lives. Okay, and those pairs were each are going to give rise to a convolution, F star G, which has certain properties, right? So if in each case, if the conditions are satisfied, then the convolution also satisfies some conditions. Okay, and so what we want to do is we want to talk about continuity in each of those cases. Okay. All right. Okay, so we want to give conditions for continuity of the bilinear mapping FG goes to F star G. Okay, and so here's what I'm going to do. What I'm going to do is I'm going to write down, all right, so B here is going to be convolution, right? So, and U is F, B is G, and so B is of FG is going to be F star G, okay? So I'm going to write down a condition like this one, all right? Because what we essentially gave last time was we gave some sometimes normed spaces, but also sometimes semi-normed spaces. In all of the cases, I'm going to give estimates like this, either for the norms or for the semi-norms. Okay, and those bounds, which look like this, the point is that you should interpret those as being continuity statements for the bilinear mapping. Okay. All right, so the 4 cases were this. Okay, the first case we looked at was when F, so let me write them in this so they'll look the same. and G. Okay, and so in this case, we had that F star G is in L1. Okay, so that was the first case we looked at. And in this case, we get a bound for the convolution. And so the convolution's in L1, and so we expect the bound to come in terms of the L1 norm, and we expect for the bound to be of the L1 norm of the convolution in terms of the L1 norms of the arguments, okay? And so indeed, you get this, and the point, you know, the point is the coefficient m here in this case is 1. Okay, right. And it turns out that in this case, 1 is the best you can do. Okay, so you can't improve the 1 there, and I say that because that's not true in some of the other cases. All right, so the second case, we had 1 over p plus 1 over q equals 1 plus 1 over r, and we had f in LP and g in LQ. All right, and that gave us the convolution in LR. Okay, and then what you expect, of course, is a relationship rather like this, except you're going to have the R norm and the P norm and the Q norm, okay? And you do indeed get an inequality which looks exactly the same. It's not obvious that that's the case. So, you know, continuity means that you're going to get some kind of a thing which looks like this, but generally speaking, you're going to get a constant here. Turns out the constant is can be taken to be 1. Okay, but in fact, 1 is not the best constant here. There are constants you can choose, which depending on P, Q, and R are less than 1. Okay, and you know, something that people think about is what's the best constant that you can choose. So there's like a constant which goes here, which you might call M, P, Q, R, and you know, finding the smallest m is something that people care about. Not me necessarily, but other people. Okay, and so this inequality here is what's called Young's inequality. Okay. All right. And so, in fact, the way this these conditions for convolvability, you know, where they sort of come from really is actually calculated in that norm bound. All right, so you start in the L1 case. Okay, in the L1 case, this bound is relatively easy to establish using Fubini's theorem. Okay, and then you ask yourself, well, what if F isn't in L1 but some other LP, and G isn't in L1 but some other LP? What can I say about the convolution? Okay, so that's where this inequality comes from, really, is trying to just expand the F's and G's for which that is true, and then you get a condition like this that comes out. Okay, so that's kind of the origins of that. You know, I presented this kind of in some ways backwards. That comes out of black magic, but it's not black magic. The way it originally arose was from obtaining an estimate like that. All right, and then we had F in L1 loc of the non-negative reals. Okay, Um, and then we had that the convolution is in, again, L1 loc. All right. And then you get an estimate, which looks rather like this, but now these spaces are no longer normed, right? They have semi-norms. And how are those semi-norms written? Well, the way we defined the semi-norms was we defined F, and then we took a compact subinterval S, and then we had the semi-norm like that, okay? Now, and so the point is that the semi-norms are indexed by compact subintervals of the positive, the non-negative reals, okay? Now, every compact subinterval of the non-negative reals is contained in some interval of that form, okay? So if you have any compact interval, you can choose T large enough so that it's contained in there. So the point is, without loss of generality, you can look at compact intervals that look like this, okay? So that's the kind of estimate we're going to get here. We're going to get an estimate that is indexed by intervals from 0 to t, okay? So the estimate looks like this. Okay. All right. All right, and then there's the last case where again we have you know, this condition still, of course, between P, Q, and R. Okay, and you have F in L, P, loc. G in L, Q, loc. And so the convolution is in L, R, loc. That's R greater than or equals 0. Okay, and then you get the expected semi-norm bounds. Okay. And the point of all of this is that these are conditions which give you continuity as a side effect, okay? But they give you continuity by expressing very explicit bounds for norms of the convolution or semi-norms of the convolution, okay? All right, good. Okay, so let's finish off by talking about discrete time convolution. Okay, or finish off today. All right. So the story here is similar to the continuous time story, but so I'm going to kind of do it a little bit fast-ish because I did do this a little bit carefully in the continuous time case, so I won't dwell on things quite so much in the discrete time case, and I want also to indicate the places where the discrete time theory is different, usually easier than the continuous time case. Okay. So for F and G in FT, okay, and sometimes I'll write FT now just to make it look like, so remember that this is just a space of, sorry, I'm here talking about, sorry, discrete time. I'm talking about, oops, Z delta, okay. And so remember that this is just a set of all functions from Z delta into F. And again, to make the notation just look more consistent than everything else, because the problem is the simplicity in the discrete time case. This thing kind of makes sense. Not kind of, it does make sense, and it's also useful and interesting. But the notation just looks different than everything else I've used. So sometimes instead of writing this, I might write little l, because that's the kind of notation we used for discrete time signals, little l loc of Z delta F, okay? Or, I might put any discrete time domain in there, okay? And so the point is that, like locally integrable functions are functions that are integrable on compact subintervals, little l loc are things that are summable on finite subsets. Finite subsets in the discrete time case are analogous to compact subsets in the continuous time case, but every signal is summable on a finite subset of Z delta, so that's why it's everything. Okay. Okay, so for discrete time convolution, you want to write down something that looks like this. Okay, and as I said last time, this is the direct analog of the integral formula for convolution in the continuous time case. Okay, and so, I said try to write, because of course it's very easy to come up with examples of F's and G's for which this sum simply will not exist. And the same example in the discrete time case works as in the continuous time case, and that is if you take F and G to both to be the function which takes the value 1 at every t. Okay, so that sum will not exist in that case. All right. All right, so so you use the same kind of notation. Okay, so we denote d of f g to be so I'm sorry, we don't really need to do this here. Remember, we had the domain in the continuous time case, and that was a set of times where in the continuous time case we had we had the integral of f of t minus s g of s ds, and then we had times t for which this integrand was in L1, and we permitted there to be a set of t's of measure 0 for which this wasn't in L1, and we still allowed convolution to exist in that case. Well, here you can't do that, right? If for a certain k this thing isn't in L1, then you're dead, right? So the d of fg notation isn't required here, and so we'll just say, oops. Right, so we'll say that fg is convolvable if this signal oh, sorry, this is J here. Okay, if this thing is in little L1 of Z delta for every K. Okay. All right, so that's the notion of convolvability. And you have the usual rules for convolvability. And so, so we have the same rules for commutativity. Okay, so I'm going to make you go back and look at the continuous time case. So commutativity, I mean that if FG is convolvable, and so is GF, and their convolutions agree. All right, linearity. Okay, so if F and G are convolvable and F and H are convolvable, then F of G plus H is convolvable, and the convolution of F plus of F with G plus H is convolution of F with G plus the convolution of F with H. Okay. And then what about associativity? So remember, associativity, I mean this property. Okay, is not generally true. Okay, so lack of associativity. Okay, so all that stuff just translates verbatim. There's one important difference, though, in the discrete time and continuous time case is that discrete time convolution has a unit. Okay, that means an identity. So there's some signal, discrete time signal, which has the property that when you convolve it with anything, you get the same thing back. And it's even true for just any F. F needs to have no particular properties. That's because U is very simple. Okay. It's equal to 1 at 0 and 0 otherwise. Okay, so you know, the graph of this very complex signal. Right, so I'm looking at discrete time signals here, so it's 0 everywhere, except it has value 1 there. Okay, so you know, this is really a discrete time analog of the Dirac distribution. Okay, and the Dirac distribution satisfies a condition, you know, sort of like that, and we'll see this precisely. Okay, and so F acts as a unit in this case, and it's kind of the analog of the Dirac. Okay, so we're going to talk a little bit about convolution of distributions, and then we'll see that in many situations you can put a delta there. Okay, but that's getting ahead of ourselves. Okay. All right, that's why, why it's sort of unnecessary to why one doesn't talk about discrete time distributions. You don't need to. It's not clear they would make sense. Okay, so if so similarly, similarly, to the continuous time case, we can define sigma of f. Okay, and this is going to be the inf of the support of f. Okay, so the largest time with the property that for all times less than that one, f is equal to 0. Okay, and this, because we're in the discrete time case, we don't have to mess around with almost everywhere. In the discrete time case, f is identically 0 to the left of sigma of f. Okay. All right, and if sigma of f and sigma of g are greater than minus infinity, then there's a simpler formula for the convolution. Okay, so the first thing is that f and g are always convolvable in this case, which is not true in the continuous time case. Just they may not even be measurable, right? So okay, so let's take f, then fg is convolvable. And there's a simple formula for the convolution, like this. All right, so this looks rather the same. It's just the discrete time version of this, as in the continuous time case. Okay, so in the continuous time case, we had an integral, over a compact interval, and here that amounts to there being a finite sum. Okay, and so the sum goes from sigma of g. Okay, so sigma of g is a time in z delta, and so that won't be an integer, and I'm summing over integers. So to turn that into an integer, I divide by the sampling interval. Okay, so if z of delta is z, then the sampling interval is 1, of course. Okay, so the sum goes from there to, and then the upper limit is k sigma of f over delta. Okay, so you should look back at the continuous time case and see that the limits on the sum here correspond to the limits on the integral in the continuous time case, right? So the point is you get f of k delta, the usual formula, minus j delta, g of j delta. Okay, and this is valid when k delta is greater than or equal to sigma of sigma of f plus sigma of g. Okay, and 0 otherwise. Okay, now one of the things that's very annoying about the discrete time case is one has to carefully keep track of exactly what these lower bounds are, because there's always a question of plus or minus 1 happening here when you do these things that doesn't happen in the and is this greater than or equal to? It really matters in the discrete time case, whereas in the continuous time case, if you omit an endpoint from an integral, it makes no difference. Okay, so it's one of the fussy things about the discrete time case that can get you into trouble, or certainly gets me into trouble. Okay, and so if sigma of f and sigma of g are both greater than or equal to 0, then we get the convolution. Again, you have to write the formula down exactly just to make sure you get it right. So the sum here is j goes from 0 to k, right? F of k delta minus j delta g of j delta. And this is true as long as k is greater than or equal to 0 and 0 and k is less than 0. Okay. All right. So then you have a bunch of cases where of pairs of convolvable signals. Okay, and so let me say it like this. So just as in the continuous time case, we have special pairs of signal spaces for which signals are for which the pairs are convolvable. And convolution is continuous. Okay, and so, rather than belabor everything by writing down in full glory all of the things that I wrote down in the continuous time case, I'm just going to sort of summarize things, and I'm going to elect to do that in a way that I've done here in the continuous time case. Okay, so I'm going to give the pairs. I'm going to give where convolution lives, and then I'm going to write down the bound for the norm or the semi-norm. Okay. Okay, so for continuity, you have the norm, the L, little L1, little LP, little LQ norms, but then in the cases that are analogous to these cases, okay, of locally integrable signals with support bounded on the left, we use semi-norms like this. So we're going to use corresponding semi-norms in the discrete time case, and so here the integrals go from 0 to t, and the semi-norms in the discrete time case, the sums will go from 0 to n. So I'll just introduce some notation for that. Okay, so for F in little l loc. Okay, so again, this means all signals, since I, am not putting anything here. That just means all signals on. Okay, so the sampled time interval of non-negative times, I'm going to denote F n p, okay, to be the p norm in this case, right? So it's the sum j equals 0 to n f of j delta to the p to the 1 over p. Okay, and then similarly, and so this is true for valid for p in here. Okay, and then of course have this. P equals infinity case. Okay, all right, good. So now I have all the equipment I need to write down the stuff. Okay, so if f is in little l1 of z delta f, g is also in little l1 of z delta f, then f star g, sorry, yeah, so as I was writing that I forgot that. Okay, then f star g is in little l1 and I have a norm bound for the convolution. Okay. All right. So remember, we had this discussion in the continuous time case of the situation here of the convolution product and some attributes of the convolution product. So one of the things we saw is that the convolution product in this case does not have a unit, okay, in the continuous time case, all right? So in the discrete time case, it does, right, that unit, okay, because that thing's clearly in little l1, all right? So that's a difference between the discrete time and the continuous time case, is that this ring, right, L1, with this product has a unit. But the ring is still not an integral domain. So there are still F's in here and G's in here that are non-zero, but whose convolution is 0. Okay, so it's a ring with a unit, a commutative ring with a unit, but it's not an integral domain. Okay, so there's some similarities and some differences with the continuous time case. All right, and then there's the PQR case, and so I'm not going to write down the conditions on PQ and R repeatedly. You can just assume that 1 over P plus 1 over Q is equal to 1 over 1 plus 1 over R. Okay, and if F is in LP, and G is in LQ, then the convolution is in LR. Okay, and you have a norm bound. Okay, and again, here the constant 1 is the best you can achieve, and here it's not. All right, and then you have the signals with support contained in the non-negative sampled interval. Okay, so F, and here there's no difference between little LP loc and LQ log for P and Q, okay? And so this situation is a little bit different in that it doesn't actually matter what you put up here. You're just going to go L log, L log, L log, okay? Right, and they're always convolvable, okay? And we already saw that up here. Okay, so this again is the difference with the continuous time case. In the discrete time case, when you put this kind of a support constraint on the supports, immediately you always get convolvability for every pair of signals which satisfy that support condition. Okay, and that's just because that sum there is finite. All right. Okay, so the point is that if f is in L log, okay, and I'm not putting a 1 there, right? That's sort of the whole point. G is in L log. Okay, then f is in L log. Oh, sorry, I apologize. These are all greater than or equal to 0. Okay. All right, so that's just always true. And you have, you still have the norm bounds for the 1 norm and the PQR norms. Okay, so you get F star G 1. Oh, sorry, I'm working in this case. So N1, N1. Okay. All right, so the 1 doesn't show up here, but when you write if you want to talk about a specific topology on here, then you do get those bounds showing up. And similarly for the PQR case. Okay. All right. Okay, so that's kind of the basic stuff about convolution. We're not finished talking about convolution. What I'll do next time is we're going to talk about what's called periodic convolution. Okay, so convolution of periodic signals. That's going to show up in our Fourier business, and then and that'll sort of finish our discussion of convolution for signals, and then I'll talk a little bit about convolution for distributions. Okay.